Hi there. I have a new question. Resonance energy, resonance structures, and hydrogenation enthalpies of benzene. How do you explain? So this is a common question actually. IB HL folks, IB SL folks, and MCAT students, people want to know about this one. So there's a bunch of students ask this. So we're going to draw this line, kilojoules per mole, the delta H enthalpy change for hydrogenation. In the hydrogenation, what you have is hydrogen gas and a catalyst like platinum, palladium, something like that, or even ranitidine. Now, so if you do a reaction, you're going to end up with your baseline is actually cyclohexane because it cannot be hydrogenated further. So you can draw the top view or the chair conformations like I drew. So they all have the same energy. Basically, it's the same molecule. Cyclohexane, ANE, remember this name, so it's all single bonds. Now we're going to make this one from this compound, which is cyclohexene, ENE. Look at the double bond. I marked a little bit smaller because the double bonds are shorter than the single bonds. Now, if you hydrogenate this on H2 and the platinum, so it'll go into cyclohexane and releasing 120 kilojoules per mole. That's for a single bond, right? So let's put this top view into a side so you can see it's exactly we're measuring from cyclohexene to the bottom of the cyclohexane energy level, right? So now that's the hydrogenation enthalpy for one bond. Now imagine if you have two double bonds, it's a cyclohexa 1,3-diene, right? So in this case, again, note that two double bonds are shorter than the single bonds. It's going to release theoretically about 120 times 2, right? Because there's two hydrogen double bonds. So therefore, it should be 240. So these 120 and 240 releasing energies are pretty reasonable. And experimentally, we can prove that. So that's not an issue. This is just to show you the trend. Now let's look at if you have three double bonds. So that's looks like this. Again, note this one. This is actually came from Augusta Kekule, and it's not symmetric. You see the double bonds are shorter, single bonds are longer. Now, if you hydrogenate this one, you're going to get 120 times 3, roughly 360, should be released kilojoules per mole. That's the expectation, right, from the first two examples. Instead, benzene combustion will give you only about 208 kilojoules per mole. Now see the difference, 360 minus 208, 150 kilojoules per mole. That's the difference. That is the resonance energy. That is caused by this one. So that means August Kekule's structure is correct, but energetically we cannot explain. So this difference is called the resonance energy resonance stability. So why? Because benzene actually has these two resonance structures. Their bonds are not different. There's no clear single or double bonds because these 6 electrons are moving around and these pi bonds moving around delocalized. So they will have a common one structure, which is the middle one. So that's why biologists draw a circle in the middle of benzene. And this one is called the hybrid structure. That is actually hybrid of the first and the second